A foundational AI model autonomously optimized the very production kernels used to serve it. By running hundreds of experiments on its own architecture, GPT-5.6 Sol successfully cut its end-to-end serving cost by 20%. The following day, the market price for the GPT-5.6 Luna model dropped by 80%. This price drop represents a mathematical subsidy produced by internal optimization, distinct from a traditional loss-leading business strategy. Frontier status is now measured by a model's ability to generate its own efficiency, moving past the previous focus on simple intelligence scaling. To measure the scale of that efficiency, we have to look at Luna's current capabilities compared to models that sat at the absolute frontier exactly 1 year ago. The new architecture operates at nearly 9 times the speed and accomplishes the exact same tasks for roughly 6 cents on the dollar. This bar chart of the agent's last exam benchmark shows that on professional work, Luna matches the older Fable 5 model at an estimated cost per task that is nearly 99% lower. A cost collapse of this magnitude forces enterprise businesses to completely redesign how they deploy artificial intelligence applications. Dropping the cost of high-quality work by 99% makes complex, high-volume AI workflows economically viable to run at scale. This data dashboard shows how every price cut maps to a specific physical optimization at the inference layer, starting with models taking a more direct path through a task. Better routing mechanisms keep compute hardware continuously productive rather than idling. Below the routing, optimized production software processes the data, generating output tokens with significantly higher efficiency. Finally, a smarter agentic harness manages context, ensuring agents avoid repeating already completed work. Inside this pipeline, Sol acted as the core systems engineer, autonomously designing and running hundreds of distinct optimization experiments. Those self-directed experiments yielded a specific result. Token generation efficiency increased by more than 15%. Working under human-led oversight, Sol also actively monitors the training runs, intervening instantly the moment anomalies arise in the data stream. For users needing raw speed, a new fast mode for Sol replaces priority processing, delivering up to 2.5 times faster speeds at twice the standard price. If you want to track architectural updates exactly like this the day they go live, hit subscribe below. This pricing table serves as a live ledger of the model's progress, mapping engineering gains directly to market costs. Leveraging these price cuts begins by defining the strict outcome, the stakes involved, and the cost of an error. In this setup, Sol acts as the high-level architect, a sparse orchestration resource used exclusively to resolve uncertainty and define the initial plan. Routing every step of a workflow through a massive model is now mathematically inefficient and obsolete. Instead, we apply outcome-matched routing, shifting the balance of intelligence and compute cost from one discrete step to the next. In a modern coding environment, you deploy Sol at the start to process the complex edge cases and lock in the architectural blueprint. Paying the premium compute cost for Sol is justified only when that raw intelligence is setting the parameters for the rest of the system. Orchestration requires a surgical application of intelligence, reserved strictly for moments of high uncertainty. Once the plan is set, the workflow decouples from the orchestration phase and hands off to Luna, the high-volume execution agent. Luna's function in that coding pipeline is narrow, implementing the well-specified code changes laid out by Sol. It then takes over the repetitive phases of the build, autonomously writing and running exhaustive tests based on the initial architecture. This rapid execution phase completely bypasses the traditional bottleneck of relying on slow, expensive, single-model processing for every single task. Outside of coding, an 80% price cut changes the economics of large-scale document analysis, shifting it from a premium research project to an everyday operation. Routine tasks like customer interaction classification can now be deployed instantly across an enterprise without fracturing the compute budget. To build this, businesses must use rigorous evaluations to pinpoint the exact moment a workflow can safely hand off from Sol's heavy reasoning to Luna's fast processing. Economical enterprise scale is only achieved when the planning phase is completely decoupled from the execution phase. A 20% drop in serving costs and a 15% gain in generation efficiency are not isolated events. They initiate a compounding cycle. Deploying more capable models shortens the technical team's path to discovering the next generation of performance improvements. The recursive implication is stark. As the model becomes more capable of working autonomously, the physical rate at which efficiency improves actively accelerates. Sustaining this feedback loop requires a dual strategy, advancing raw capability and systemic hardware efficiency in tandem. This compounding efficiency is the mechanism required to push advanced intelligence toward global abundance. A self-optimizing system weaponizes its own efficiency against the market, bending the cost curve faster than traditional hardware iterations. We are witnessing a specific anomaly. The software is engineering its own price reduction. If a model's very first autonomous optimization drove an 80% collapse in market pricing, what is the mathematical limit of its next revision? Who is still going to be able to charge a premium for basic intelligence a year from now?